So, first of all, thanks Ariane, thanks to all the organizers, thanks for inviting me here. I always enjoy being at HES. It's a great place, and I spent a lot of time here in the past, so it's really great. What I'm going to talk, so my talk will be a bit introductory, and probably some of you know quite well what I'm going to talk about, but I'm also speaking for the ones who don't. The initial problem was indeed counting surfaces. How can you count certain types of surfaces? And I will give many examples of that. And there is a beautiful mathematical structure that emerges from that. It's called the topological recursion. It can be, so it corresponds to this picture, and basically my goal will be to explain this picture. I will start by a first example, which is to count discrete surfaces. So surfaces made of polygons. Surfaces made, it's very sensitive. Surfaces made of polygons like that, or also it's called maps. And it's called maps because you can think of a map of the world as made of different polygons that you glue together by their sides. So this will be my first example. It's counting maps. In fact, the first one to count maps was Tutt in the 60s, and he was counting the following problem. So let's address the following question. You glue quadrangles. In how many ways can you glue a certain number of, let's say, n quadrangles, such that topologically you get a sphere? For example, okay, I have several quadrangles here. Okay, if you take one quadrangle like that, and there will be a rooted edge somewhere on the quadrangle. But just let's start with n equals 1. One quadrangle. If you glue this side to this side, then this side to this side, you get a torus. It's not a sphere. In how many ways can you get a sphere? Okay, I will show you. If you glue this side to this side, on this side to this side, okay, topologically it's a sphere. And the marked edge is there. So we have glued the marked edge to the edge following it. But you could glue the marked edge to the edge preceding it, and it will be a different gluing. So the answer is 2. And in fact, Tutt found the general formula, which is written here. So if you have k quadrangles, the number of gluings to get a sphere is that number. Okay, nice. And here are the first few. So I showed you the 2. So this is what I just showed you. The 9, if you want. So I have 2 quadrangles. So also we glue oriented surfaces. So the surfaces have 2 sides, and you can glue them only with the same color, not the opposite color. And there are some quadrangles that, so one of the quadrangles has a marked edge. This is the rooted map. And the other quadrangle has no marked edge. Gluing it this way or this way is the same. It's counting as only one. Okay, and here typically to get the 9, one possibility is just to glue these 2 quadrangles together. If you inflate, this is a sphere. Okay, that's one possibility. This is the one on the here. So in fact, I draw one quadrangle as the interior, and the other quadrangle is the exterior on the sphere. Another possibility would be that you can do, for example, this, and you glue the other one there or there, and put the arrow in all possible positions, and you get 8 possibilities that are there. And in total, there are 9 possibilities. So the number is 9. Okay, now let's make, sorry, what's wrong? Let's make a generating series. So let's put all these numbers together to form a generating series. So this series, can you read? Okay, so this series, maybe you recognize it at once. Okay, it's the Taylor expansion of a certain function which involves the square root of 1 minus 12t. Okay, I will write it, I will use the variable r, which is square root of 1 minus 12t, because in that variable r, everything will be rational. So it's convenient. Later, I will call it So this map from T to R, and since in R everything will be rational, this map, I will call it the mirror map. Okay, for those who know mirror symmetry and things like that. Okay, it's just a kind of preview. Now let's, in fact, how did Tutt prove this formula? He solved a slightly more general problem where we don't have only quadrangles, but we start having faces of different size. For example, here we have an hexagon. And in fact, let's solve the following problem. You have k unmarked quadrangles, sorry, k unmarked quadrangles, so here k equals 4, and one face with a certain number of edges on the side. And if you think about it, it has to be an even number, because you are gluing quadrangles, you must have an even number. And let's call it 2l equals 6 in this example. In how many ways can you glue a hexagon which has a marked edge on its side and 4 unmarked quadrangles in order to get a sphere? And the answer is 225. Okay. In fact, there is again a formula which was found by Tutt, and this is the formula. Now again, make a generating series. Now we sum over t to the k for the number of marked, unmarked quadrangles, and z, 1 over z to the 2l plus 1 for the boundary size. And we resum this series and we realize that this is this function of t and z. Okay. Again, I use the variable r, which was square root of 1 minus 12t. Now let's look at this function as a function of z at fixed t. In fact, I will, in all what follows, t and z will play slightly different roles. T will, basically, I will have to write equations, but the equations will really be equations in z, and t will be like a spectator parameter. It will play really no role. In fact, z, the combinatorics call it a catalytic variable, or people in integrable system will call it a spectral variable, whereas t is called a time or something like that. So, anyways, let's look at this y as a function of z. Let's plot that in the plane. So you see, you get an algebraic. So this is an algebraic curve. It satisfies an algebraic equation, which you can write as a polynomial. It's also a polynomial in R. So you can write such a polynomial equation. But now, in fact, you should not think of it as a one-dimensional curve in the two-dimensional plane. You should think of that in terms of complex. So when I say one-dimensional curve, I mean one-dimensional complex. So which means that you should not plot it in R cross R, but in C cross C, which is R4. And in R4, you have one complex function of a complex variable, which is like two real functions of two real variables. So in fact, in R4, this is a surface. So, yes, so it's okay. In R4, in fact, if you could make the plot in R4, you would see a surface. And this surface can have a certain genus, it can have a certain topology, it can have cycles, it can have things. And in fact, this one is of genus 0. In fact, my picture here is not that good. In fact, this picture corresponded to another enumerative problem. But so it's a surface, and this one I can tell you has genus 0. And let me call this function of z, let me call it W01 of z on t. So as I said, t will play a role of spectator, and very often I will not even write the t, I will only write that it's a function of z. So why do I call it 0, 1? 0 refers to the planar maps. Later I will consider maps of genus 1, so on and so on. And the 1 refers to the fact that we have one rooted edge, one marked edge. And so we have found this surface. So Tutt has found this surface. Okay, now we have this surface. Let's try to solve other things. So now let's look at the quadrangulation of spheres. Let's try to enumerate quadrangulations of spheres, where there is, in fact, now we have two marked faces with one edge on their boundary. Okay, two marked faces of two lengths, L1 and L2, and instead of L1 and L2, let me use these two variables A and B. Formulas will be nicer if you do that. on k unmarked faces. And again, in how many ways can you, so how many such gluings do you have? So it's an integer number, and there is a formula, which is that one. Okay, this one I don't think it was found by Todd, but okay. But now we know the answer, and this is what you get. So it's a nice formula. Again, you make a generating series. Now you have still t to a k, but you have a z1 for coupled to L1 and z2 coupled to L2. You resum this series. Well, you call it W02. Now again, 0 because it's planar, and 2 because you have two marked faces. And let's see what it is. It is this function. Okay. Okay, it's an algebraic function. Nice. Okay. But in fact, this function is not at all an arbitrary function. In fact, you could have guessed it from the very beginning. Basically, as soon as you know W01, you could have guessed that W02 should be equal to that. So I have to say, what is this function on? So it will be related to a so-called green function or fundamental second kind differential or Bergman kernel. It depends on the context in which you are to call it in this way. So let me recall. We have already computed W01, which is a Riemann surface. Okay, and what I want to tell you is that W02 is some geometric property of that surface. It can be seen from the geometry of the surface. There is a nice analogy which is electrostatic. Imagine that you play, so this surface is in R cross R. It inherits the matrix, it's in C cross C. It inherits the matrix of R4. And there is typically you have a Laplacian on that surface, and you can solve the equations of electrostatics. Poisson equation, Laplacian equals delta function. And you solve it on the surface, and basically the solution is the electric field. So now let's ask the question. You place at a position, let's say Z1, at Z1 here on that surface, you place an electric dipole of unit charge. And you want to know what is the electric field measured at a position Z2. And this is the formula. Okay. And basically this W02 is the electric field of a dipole. So you place a dipole at position Z1 and you measure the field at position Z2. A field is, so a two-dimensional vector field can be represented as a complex number, and this is this complex number. Okay. So basically the idea is that knowing W01, you can immediately guess what is W02. Now let's generalize that to more to higher number of marked faces and even higher genus. So now, can you count the number of maps with a given genus and a given number of marked faces with given lengths L1, L2, Ln? Okay, and again, we make a generating series, WGN. It depends on n variables coupled to the length of the n boundaries, and the t coupled to the number of unmarked quadrangles. And you would like to compute this function WGN. So, can you compute it? And again, in fact, it is completely, it can be obtained just by the geometry of the surface which you had for W01. And there is a recursion. So let me show you this recursion. So no, first let me give you some examples. So first let's start by 3 marked faces on the planar. Since it's planar, instead of drawing it on the sphere, you can draw it on the plane. On the one of the marked face is the one on the exterior. So this is this picture. You have in fact 3 faces. One is the blue at the exterior here. Okay. And so what is the result? The result is the following. So you see this formula. So it's a residue. But so you see, we have already computed W01 and we have already computed W02. And here we have our 3 variables Z1, Z2, Z3. So the formula works as follows. Take W02 of ZZ2, multiply by W02 of ZZ3, multiply by 2, multiply by this big quantity here, and take the residue at Z equals, well, basically at the zeros of this square root here. Okay? And so you have a sum of two residues, one at z equals plus square root, one at z equals minus square root. You add the result, and what you get is W03. Okay, it may look strange because Z2, Z3, and Z1 seem to play very different roles, but this function is indeed symmetric. Now let's look at another case, which is one boundary on one handle, so genus 1, I call that the lead. And here is a formula for W11. Again, basically it looks very much like that one, residue at exactly the same point, the same prefactor. The only thing that changes is what you have in the bracket. Instead of this thing that involved Z2 and Z3, here you have a W02 of ZZ. And Z is the variable on which you integrate to get the residue. So you see the formula looks very similar. And in fact, in general, what you get is always something like that. Every double Gn plus 1 can be written as a residue at the same points with the same prefactor and multiplied by, and the only thing that is different in each case is what you have in the bracket. And in the bracket, what you have is a combination of W's that you have somehow already computed at previous steps. So it's a recursion. It's a recursion that allows you to compute all of them. And so basically, the idea is that once you have computed W01, you get W02 as this electrostatic field, and then you get all of them by this formula. Now, this formula works for quadrangulations. It would also work for triangulations. The only difference with quadrangulations is where you take the residues, and this prefactor would change a little bit. But more or less, it's the same formula for triangulations, for also, if instead of putting quadrangles, triangles, you would put pentagons, hexagons, whatever. I mean, any kinds of map, even maps with colors, quadrangles of different colors, quadrangles carrying a POTS model, an ON model, the same formula would continue to work. And it's called the topological recursion. And topological because it's a recursion on the topology, because you can check that all the W's that are in the right-hand side have a Euler characteristic, which is one less than the left-hand side. I mean, one less in absolute value, because the Euler characteristic is negative. And let me represent this operation. So multiplying by the prefactor and taking the residue, let me represent it as an operator kernel acting on the bracket. Okay, so this is what you get for maps, for counting maps. You have this kind of universal formula which works for counting many different sorts of maps. Now let me, so this is just what I just said. So it's a recursion on the genus. And okay, there is a nice way to represent this formula. So think of the terms that you have in bracket here. So you want to compute WGN plus 1, so maps of genus G with n plus 1 marked faces, or which I call boundaries. And you would like to compute this function. And the formula tells you that, well, you have to compute WG minus 1 n plus 2. And if you think of it, you have to take, so G minus 1, and you have n plus 2 boundaries, so n minus 1 here, plus 2 at which you put variable z and z. And you multiply by k, which depends only on z1 and z. And if you think of it, it's like starting from there and removing, well, a pinched pair of pants. I prefer, so some people say removing a pair of pants, but I prefer to think of pinched pair of pants because in fact there is only one independent variable, not two. So you should not think it's really two boundaries, but only one boundary which is pinched. Well, okay, that's my point of view. And the other term, this sum, is the sum of all the possible ways to, again, remove this pinched pair of pants. And so what remains can be, so it can be either connected of genus minus 1, or it can be disconnected with a part of a genus there, a part of a genus there, and a part of the boundaries there, and a part of the boundaries there, in all possible ways. The only restriction that I put in this sum is that I don't allow disks. I never allow disks on the right-hand side, but then it's a recursion. Okay, let me now go to another counting problem of surfaces. Let's now count hyperbolic surfaces. and let's try to see if we can enumerate hyperbolic surfaces. This is the problem. So this problem is very linked to the notion of to names of Weil and Peterson, who basically said how you should enumerate. But Mariam Mirzakhani, she got the Fields Medal because she found a formula to enumerate, a recursive formula. And also this problem is very fashionable recently in physics because it has application to black holes, to the Jackiw-Teitelbaum black holes. And this is very, this counting problem is very used in trying to compute the entropy of black holes on amplitude, diffusion amplitude in black holes. It's very fashionable at the moment. So let me explain what we are talking about. So let MGN of L1, Ln be the set of surfaces with a metric of constant curvature -1, so hyperbolic surfaces, and such that there are n boundaries that are geodesic and of prescribed length, L1, Ln, and they are labeled boundaries. And in fact, I should have said, in fact, it has disappeared from my side, but quotiented by isometries, modulo isometries. And here is a typical example. And there is a way to, so the number of such objects is infinite, and instead of counting such objects, we shall put a measure on this space and compute the volume. Okay, and it's called the Weil-Peterson volume. Well, the way to do that is that, in fact, every hyperbolic surface can be decomposed into elementary pieces that are pairs of points with geodesic boundaries. And so you choose typically 3 closed geodesics that cut your surface into pairs of points, and you see what are the lengths of those internal geodesics. And vice versa, you can reconstruct every element of this MGN by gluing pairs of points. So imagine you take 3 pairs of points like that. To glue them together, of course, the length must be the same. The length of the boundary must be the same, but then you can rotate by some angle. There is a rotation angle that is free, and basically, locally, the coordinates, the length and the angles are a local system of coordinates in your space MGN. And Weil-Peterson showed that this measure, product of DLD thetas, is independent of how you cut into pairs of points, and it gives a well-defined volume form on your space, and now you can integrate that on the space, and this defines the volume. Well, first of all, it's not totally obvious that this volume is finite and not infinite, and it's not obvious at all what it will be and how you can compute it. First, you have been computed. Well, in fact, V03, M03, it's the case where there is, if you have prescribed length, there is a unique pair of points with prescribed length. So in fact, M03 contains only one element, and the volume is 1. Okay. But the others, like V11, is much more tricky to compute. And the main difficulty, so I will tell what, but basically, it has been computed by hyperbolic geometers, and they found this answer. So, okay, this is also V04, it has been computed a long time ago. It's quite surprising that it's a polynomial in the length, an even polynomial in the length. And it's not obvious from the definition. The main difficulty in doing this computation is that the decomposition into pairs of points is not unique. Just, for example, in this example, you have 2 geodesics in which you could cut, or in this example, you could have chosen this geodesic, or even that one. And in fact, there is an infinite number of ways to decompose. And basically, the main difficulty is to avoid the double counting, or to take care of this double counting, or multiple counting, and that's very tricky. That's quite hard. And this is where Mariam Mirzakhani found a solution. And but before giving Mirzakhani's formula, I will in fact do the Laplace transform of the volumes. So I will Laplace transform the volumes. So I take the VGN, I multiply by e to the minus zi li, and integrate from 0 to infinity. I also multiply by L. And this defines the function WGN. Well, here I've written a small summary. The idea is that whenever you have L to the k in this Laplace transform, it becomes 1 over z to the k plus 1 times k plus 1 factorial. So it's very easy to see what v03, v11, and so on, what they become. Since they are polynomials in the Li squares, in the right-hand side, you get polynomials in the 1 over zi squares. Okay, and the question is, can you compute these? And here is Mirzakhani's theorem from 2004, and which we Laplace transformed with Orentin. In fact, Mirzakhani's theorem involves integrals from 0 to infinity, and in Laplace transform, you only have residues. This becomes residues. But here is the formula. So there is a certain, and you see it looks very much like the recursion we had for maps. Very, very much. But the kernel is different. It is just 1 over this sine function, basically. There is a residue at 0, whereas before I had 2 residues, but now we have only 1. And we take this W02. Okay, I'm going to show you. So first, it's a recursive formula. It allows to compute all the volumes. And it allows, for example, to prove that all of them are polynomials in the square length, which was not, I think it was not known before. Okay, and again, it's illustrated by the same picture. Let me show you how this theorem, let me show you on the example of W11, how you can use this theorem. So again, hyperbolic geometers have computed that this is the volume. You do the Laplace transform and you get that. This is what I've written here. So this computation is the computation from hyperbolic geometry. And basically the hard part is to find that, and I'm not going to give you the proof, it's hard. You have to work a lot to get that. But let me show you how you can get the same result here by using this theorem. And you see here that it will be much, much easier. So let's use the theorem. So W11, according to the theorem, is that, and if you look at what you can have in the right-hand side in the bracket, the only possible term is W02 of z and minus z. So now you replace W02 by that, so this becomes 1 over 4z squared. You replace the k by that, okay? So you have to compute this residue, so basically you need to do the Taylor expansion at small z. It will be quite easy. Let me put the prefactor 4, the pi, the 2 pi, the z1 square in front, so that makes a 1 over 8 z1 square. Then you have a 1 over z cubed, because there is a z coming from the side, a z square coming from there. There is this there, and this is the expansion of a 1 over the sine function, okay? And basically the residue just means you have to pick the coefficient of 1 over z. So basically the coefficient of z squared in this formula, and this is just this one, and you just get that. And you see the most complicated part of the computation was basically the Taylor expansion of the sine function. And so it's much, much easier than doing hyperbolic geometry. So this was a big progress, and then also, since it's a recursion, you can prove many, many things by recursion using that. And you can even discover new results which were not known in hyperbolic geometry by using this formula. So this was a great progress. Okay, let me mention, okay, let me move forward. So let's summarize. Once you know, okay, this is for maps. You first compute W01, so planar maps with only one boundary, and this one is not given by the recursion. It will be the starting point of a recursion. So this one, W01, is given by, given by Tot, given by God, whatever. Okay, someone has to compute it. Okay, someone has to compute W01. Someone has to tell you what is W01. Then, once you have W01, W02 is just this fundamental form. Okay? And then, every WGN are given by this universal recursion formula. The only thing that changes in the formula, no, in fact, this formula depends on nothing. Here, the K is always given by the same thing, so it depends on W02 that you have already computed as the fundamental form, and the denominator is the difference of W01 in the first sheet and W01 in the second sheet. Something like that. Okay. And then you take residues that basically you have to take residue where the denominator has a pole. And this is a universal formula. There is no parameter in it, and it works for all types of maps. It also works for the Mirzakhani's case, so it works for many cases. But now the question is, okay, here W01 was given by people who computed a number of surfaces. Now, can you do the same if you start from an arbitrary function? Take your favorite function, W01 of Z, take, I don't know, Lambert function, for example. Okay, it's not, okay. So what would you get if you take the Lambert function? Well, I can tell you, you will be computing the Hurwitz numbers. Okay, the simple Hurwitz numbers. Okay, and there's many such examples. And I will show you later that if you take W01 to be the mirror map, the mirror curve of a certain Calabi-Yau, you will be computing the Gromov-Witten numbers. Okay, and if you take just y equals, so if you take just square root of z, you compute the Witten-Kontsevich intersection numbers, and so on. And so, in fact, this has, so there are many things that satisfy the same universal recursion, and all of them have beautiful properties. Now, but one of the questions, if I take now an arbitrary function, just look at the recursion here. You see that Z1 seems to play a very different role from every other Z2, Zn. It's clearly, this formula is clearly symmetric in terms of Z2, Z3, and so on, Zn, but it's not clear at all that it's also symmetric in Z1. When you were computing surfaces, I mean, you know beforehand that what you will get will be symmetric because this was the definition. But here, if you start from an arbitrary function, is it guaranteed that you get a symmetric function? And in fact, the answer is yes, and this is proved by recursion, by the way. And the answer is you always get something symmetric. So, which means that this nice form of a kernel is not arbitrary at all. It's what you need. Okay. So now, let's indeed take an arbitrary plane curve. Well, here P can be a polynomial, but in fact what I just need is, let's say, analytic function. It needs not be a polynomial. For example, for the sine function for Mirzakhani, the sine function is clearly not a polynomial. So let's call that a spectral curve. And basically, if you look at y as a function of x, this is the W01. And if you look at the, so that's what I say, W01 is y as a function of x. In fact, I prefer to make it a differential form, so I multiply by dx. It's more geometric, more intrinsic. Then W02 is a fundamental second kind differential. And then recursively, you take this same formula, the same formula as before, and you compute recursively some WGNs, and you call WGNs are called the invariants of a spectral curve. Okay. So basically these procedures associate to any spectral curve a sequence with two indices of invariants. And as I said, they are symmetric, which is not obvious from the definition. You have to prove it, but it's proved. They are always symmetric. And just a remark, when n equals 0, it's a function of 0 variable. If you want, it's a scalar, and it's customary to call it fg rather than wg0. Okay, it's just because I'm probably going to use this notation later. And they have many beautiful properties, these invariants. Well, so it's just a list. They have modular properties. In fact, they are not modular invariants. They are more like quasi-modular forms. Almost modular forms.
I ask you, this procedure of gluing more and more complicated surfaces by recursion, is it unambiguous if you start from quite complicated, algebraic, but quite complicated Riemann surface with many sheets, many concepts?
Yes, more or less, yeah. Hmm? Yes. Yes, it is.
Where do you compute the residues in this case?
Okay, we can discuss that later.
Okay.
I don't want to go too deep in the technical details. Okay. Okay, so they have beautiful modular properties. but I will not, I'm just giving the word modular because modular invariants are very beautiful objects in mathematics, and these are. Or there are some computations of WGNs that are modular invariants. They satisfy equations of the type Cyber-Witten. They are related to an integrable system. You can always build an integrable system, a formal integrable system from these objects. They satisfy Virasoro or W-algebra equations. And they have nice properties of continuity when you deform your spectral curve and so on. And they are really beautiful mathematical objects. In fact, they are extremely fascinating mathematical objects, and now it's become nearly there is really a field of topological recursion in mathematics. So I want to show you one more example, which is Gromov-Witten invariance. I'm not expecting everyone to know what is Gromov-Witten invariance, even if we are at ITS and Gromov is at ITS. But I'm not expecting, so I will give a kind of idea of what are Gromov-Witten invariants in a nutshell. I will start from a very, very basic example. And I will ask the question, through 2 points, how many lines, how many straight lines? I think everyone should know the answer. 1. Okay. Now let me ask the question. How many curves of degree 2 through 5 points in the plane? Well, you can call it conics, but basically any equation of degree 2. How many of them? So it was a theorem of, I think, Blaise Pascal, who proved that there is a unique one. Okay, there is a unique degree 2 curve through 5 points. And how many rational curves of degree 3 through 8 points? Okay, this one probably you don't know. The answer is 12. There are exactly 12. If you take 8 points in generic position, there are 12 degree 3 rational curves that can go through them. And more generally, if you ask how many rational curves of degree D pass through 3D minus 1 points in generic position. Let's call that number N0 of the plane, CP2. In fact, I'm talking about the complex plane. I was cheating you a little bit in my picture, of degree D. And this is a number. Okay. And so the first two are 1, 1, 12, and 620, blah, blah. Okay, they are big. And the question, how can you compute them in practice? Okay, this is a definition, but it's not useful to compute them in practice. So the idea is you would like to get a recursion. Okay, and in fact, I think it's Maxime who found the recursion for that case. Maxime Kontsevich. Okay. In fact, so the word rational was important. Rational means that when you write this curve in C cross C, it's a surface, and rational means it's a surface of genus 0. Now ask the same question. Now take a surface of genus 1, it's called an elliptic curve. So how many elliptic curves go through 3D points in CP2? And here, so let's call this number N1 now. So N0 was for genus 0, N1 is for genus 1 curves. How many genus 1 curves, how many elliptic curves of degree D through 3D points? And, well, elliptic curves must have degree at least 3. There is no elliptic curve of degree 1 or 2, but it starts at 3, and then these are these numbers. Okay. And in fact, this is an example. So all this is an example of Gromov-Witten numbers. And in general, what is Gromov-Witten numbers of a certain target space X on degree beta on genus G? What is NG X beta? It's the number of ways to immerse Riemann surface of genus G holomorphically into your target space and holomorphically with a degree beta, which is in fact a cohomology class. And going through a certain number of generic points so that you will get a finite number. Okay, so this is the definition of Gromov-Witten invariance. Let me take now X a Calabi-Yau space. On beta, the degree is in fact a cohomology class, okay? And again, look at this space of all possible ways to embed, so all possible functions from a surface of genus G into X that has class beta. And let's call the Gromov-Witten invariance the number of such holomorphic embeddings, holomorphic immersions. So, in fact, I will need to enlarge a little bit the problem to have surfaces with boundaries, and that's called open Gromov-Witten invariance. What I'm giving is not a very precise definition, it's just the idea of the definition. But the idea is, again, you want to count in how many ways you can embed a surface of genus G with n boundaries into X. But in order to enter the boundaries, you want them to end in a certain locus in X that is called, well, physicists would call that a brane, mathematicians would call that a special Lagrangian submanifold, but basically it's the same thing. So you have to put the boundaries on this special Lagrangian submanifold, and in how many ways can this be done? And this can depend on the degree of your surface, on the degree of embedding, beta, and in fact, when you embed the boundaries, so the boundaries of your surface will end up on your brain, but they can wrap the brain many times. So there is the degree of the boundaries is the winding number. Okay, and so again, you would like to and now ngn xl beta w is the number of ways to do that, and that's what you would like to compute, this Gromov-Witten invariance. And again, you make a generic series and multiply by, so to make a generic series, you will sum over all the possible degrees, put t to the degree beta, a little bit like I was doing for maps, except I put it in an exponential. And for the boundaries, again, instead of writing 1 over zi to the length, let me put exponential wi zi. Okay, and let me make this generic series. Okay, and question, how can you compute this WGN? And the answer is by topological recursion. So, the answer is they will satisfy the same recursion as before, but with a certain, but you have to know what W1 you should choose, W01 you should choose, so what spectral curve, and the spectral curve is the mirror of your Calabi-Yau manifold, X. So, in fact, this was really proved only for when X is a special kind of Calabi-Yau manifold, which is a toric Calabi-Yau manifold. In that case, this was proved. In fact, in the other cases, it's a conjecture. There is nothing that indicates that it's wrong, but it's too hard to answer at the moment. But for toric Calabi-Yau threefolds, the advantage is that the mirror of a toric Calabi-Yau threefold is a curve. And is well, okay, it's not exactly a curve, but it's a certain bundle over a curve. But there is a curve in a singular locus of a toric Calabi-Yau threefold is a curve. You call that the spectral. You take that as a spectral curve, and then it turns out that this is the curve you should use to compute all the WGNs by this recursion, and this works. Okay, so it's a proof. So this is in fact a proof of mirror symmetry to all genus for that problem. Okay, I'm arriving to the conclusion of my talk. In fact, I have backslides too, but okay. So the topological recursion is, so let me summarize what we have. The topological recursion is a universal equation which is satisfied by many enumerative geometry problems. So maps, Gromov-Witten numbers, hyperbolic surfaces, so JT, black hole gravity, Hurwitz numbers. I could cite many other examples that are not that I have not shown you. While computationally, basically you can just encode this kernel on a computer, and you just have to press the button. Of course, it's not that fast, and there are sometimes faster methods. But you have to use extra knowledge that you know about your problem, but at least this one will always work, and you can just close your eyes and press the button and it will always work. Maybe it's not very fast, but it will work. Maybe you have a faster method on your own, but which is more problem dependent. This one is universal. Also, another thing is that they define mathematical invariants associated to spectral curves and that have many beautiful mathematical properties. Basically, I think that every beautiful mathematical property you can think of in mathematical physics is there. Okay. Yeah, that's true. Okay, if you think that you know a kind of property that is not there, we could discuss together. But probably it is. Also, it has many applications, and I've shown you a few applications so far. But just to give you a hint, this is related to knot theory. Basically, if you do the asymptotic expansion of Jones polynomials, the coefficient of your asymptotic expansions, it is a conjecture, it's not proved, but they are expected to satisfy the topological recursion. At least this was verified for some knots, like the figure 8 knot, it was verified to several orders, and it works. Another thing is random matrices. This conference is about random matrices and physics. I've talked a little bit about physics. I didn't talk about random matrices so far, but in fact they were here all the time because this recursion was initially discovered in the context of random matrices. This recursion came from random matrices, and random matrices are very related to the enumeration of maps. So in fact, random matrices are there. And so this is just the histogram of eigenvalue of a Gaussian random matrix, the famous semicircle, Wigner semicircle. Another example is crystal growth. So you know, it's called also plane partitions of three-dimensional partitions. It has also something to do with this problem. In fact, it is known that it has something to do with Gromov-Witten invariance, or more precisely Donaldson-Thomas invariance, but there is this duality to Gromov-Witten. Okay. So this is, yes, so I also mentioned a little bit integrable systems like Hitchin systems and also module spaces of connections. I didn't talk about intersection numbers, but we have some kinds of Gromov-Witten numbers anyways. So this is just to give you a hint of things that can be done through topological recursion. And just in fact studying topological recursion on its own is interesting. So this is the end of my talk. Just in case you'd be interested, please know that I have some slides about nodes, about random matrices and other things in case you'd like to ask. But so we can stop there. Oh. Okay, thanks.
So thank you very much for this nice talk. Are there any questions?
Yes, thanks for the very nice talk. So perhaps a very stupid question, but I wonder if there is a way to use topological recursion, for example, to gain some correlation functions with arbitrary genus in some say holomorphic in some two-dimensional conformality theory. So whether you start with a simple correlator, like an holomorphic correlator of the stress tensor, and you forget but if the answer is yes, in which limit do you get this correlation function?
Typically, so since we get a recursion, it's good for computing typically asymptotic expansions. So in fact, topological recursion, what it would compute is an asymptotic expansion of correlation functions or amplitude in a CFT. And the parameter of expansion, so you have to ask the question, what is the parameter or what is the regime in which you do the expansion, and it's the heavy limit. Basically when all charges are large. So this is the limit where all charges are large, and this is when you get topological recursion. In fact, this was my next slide. Okay. Maybe, okay, I think I don't want to enter too much in the details. So let me, okay. Think of the WNs as an insertion of n currents. And then you would like to expand that at large charges alpha i's. So multiply every charge alpha by a parameter. And I think yes, Well, okay. Or somehow I'm doing an expansion at large Q, I think. Sorry. No, I think this is a bit wrong, what I have here. Let me not show it. But basically, this is it. Wn, think of Wn as the insertion of n current operators, and do an expansion at large charge, and the kth coefficient will be Wkn. And this satisfies, and basically, topological recursion automatically satisfies the bootstrap axioms. So topological recursion, it's very, very easy to see that it satisfies OPEs and word identities. What is more difficult is the crossing symmetry, but basically this is related to the integrability property.
In that case, you are not changing the topology of the space, right? Just wonder. So you get correlation functions in, for example, in flat space.
You can choose your space.
Okay, good.
It would work for every Riemann surface.
Thank you.
And this is why it's related to Hitchin systems, by the way.
So I have a question. So you applied your theory to chromovital invariants. Does it mean that for every Calabi-Yau you can construct a spectral curve?
Well, toric Calabi-Yaus, yes, you use the Oriva-Farah construction. For non-toric Calabi-Yaus, like the quintic, the answer is more subtle. Okay, in a certain sense, yes, and that's called a local spectral curve, but it's not an algebraic equation, let's say. Okay, so in fact, the mirror of a non-toric Calabi-Yau or a compact Calabi-Yau, for example, is really a three-dimensional manifold. It's not a curve. So you have to work a bit, but yes, the answer is yes in a certain sense.
There's a plot of random tiling things.
Yes.
What's the story there?
Again, so in fact, you see, that's what this picture represents. Take a vertical line, any vertical line, and plot, make a blue plot. So you see these blue dots correspond to every vertical edge that you meet. Okay? Every vertical edge. Okay? And think of these as the eigenvalue of a matrix. And so basically, since you think of, let's say, the time variable going from left to right, and at each time, so each vertical line corresponds to a certain time, and you have a time-dependent matrix with spectrum. Your tiling is a random tiling, which means you have random eigenvalues of your, you have a random matrix model. In fact, you can find a random matrix model that corresponds to that. And when you are in the large size limit, you can do an asymptotic expansion, and basically it obeys topological recursion. And the spectral curve is somehow the limit shape, this cardioid or whatever. The spectral curve is the limit shape. It's the Okunkov, okay, it's the lowest degree curve that is tangent to all boundaries or something like that. Yeah. On the fact that, okay, on the fact, sorry, the spectral curve can also be thought as the kind of, okay, if you plot the histogram of such eigenvalues, you get a eigenvalue histogram, so it will not be a semicircle, it will be something more complicated, but basically, asymptotically, this will turn to a curve. And for each vertical edge, you will get a different curve. And so, it turns out that each of them can be used as the spectral curve of your problem. And the fact that the omega GNs, the expansion of the partition function is the same whatever time you choose, it's because all these lines, so these limit curves at all the lines are related together by the Burger's equation. Because asymptotically, this is a kind of Burger's fluid. You probably know that, it's Burger's fluid. And this means that, and this is equivalent to saying that the different spectral curves that you obtain for different times are related by a symplectomorphism. And the invariants that we build are precisely symplectic invariants, which is a conjecture, it's not fully proof.
Are there Any more questions? Well, if not, let's thank Bertrand again.